3I Atlas should be fading into silence by now, a cooling shard of interstellar ice drifting 186 million miles from Earth, surviving on the last thin scraps of sunlight. At this distance, comets don't flare, they don't fight, and they definitely don't reshape themselves into structures so precise they look engineered. Yet the newest high-resolution images show exactly that: laser-straight twin tails, impossible density ratios, and a behavior pattern that even Avi Loeb's calculations cannot fully explain. His latest numbers point to something almost absurd: an anti-tail 1 million times denser than the solar wind pushing against it. So the question that everyone is trying to avoid becomes unavoidable. What exactly is 3I Atlas doing out here? Out at 186 million miles, sunlight falls weakly, just 300 watts per square meter, barely a whisper of heat compared to Earth. This is the deep outbound track of an interstellar comet, now drifting through the cold outer reaches of our solar system. At this distance, a comet's activity should be fading quickly. Jets cool, brightness drops, tails collapse and thin out. That's the script every normal comet follows. But from the moment 3I Atlas was first spotted, it refused to follow any script at all. Even long before it approached the sun, it was already misbehaving. In May and June 2025, NASA's test satellite caught the comet unexpectedly active at $6.44, almost 600 million miles away. A region so cold that water ice should be completely frozen, incapable of sublimating. Yet Atlas was brightening, shedding material, acting like a comet much closer to the sun. That early activation was the first sign that something was fundamentally wrong, or fundamentally different. The energy available at that distance was far too low to trigger typical comet activity. So something else had to be fueling it. Possibly CO2 ice, or even more exotic ices capable of vaporizing at extremely low temperatures. Whatever it was, it meant Atlas wasn't playing by normal rules. As the comet continued inward, its sunlight exposure jumped from under 20 watts per square meter to 300, still only a tiny fraction of what Earth receives. And yet, instead of calming down, Atlas became even more active, even brighter. It refused to quiet, refused to fade, and refused to behave like every model predicted. This is what first drew Avi Loeb's attention. The activity didn't match the available solar energy. The numbers didn't line up, and the object seemed to be ramping up, not cooling off. So when the new images came in, the puzzle deepened dramatically. On November 22nd, astronomers using a half-meter telescope captured the clearest view yet of 3I Atlas, a tight, compact coma flanked by two incredibly narrow, needle-straight tails. One stretched almost 3 million miles away from the sun. The other, the anti-tail, extended 600,000 miles toward the sun. The geometry held steady in a second image taken on November 24th, despite poor viewing conditions, and multiple observatories confirmed the same view. No camera glitch, no lighting illusion. Something genuinely strange was happening. Comet tails, under normal physics, don't act like this. Dust and gas from comets spread out into broad, wispy fans as the solar wind tears through them. They diffuse, twist, fragment. But Atlas tails remain astonishingly straight, tight, collimated, like two beams, locked in position over millions of miles. Even amateur astronomers with small telescopes reported the same impossible symmetry. The ratio between the tails was even stranger, a perfect, persistent 5:1 length ratio. The anti-tail was always 1/5 the length of the main tail, and it never changed. That level of geometric consistency has never been recorded in a natural comet. And then comes the most puzzling detail: the anti-tail pointing toward the sun. For dust and gas to flow upstream against the force of the solar wind, the material must be unbelievably dense. Loeb's calculations confirm this. The anti-tail must be 1 million times denser than the solar wind around it. No normal comet can produce a stream that dense. Solar wind should scatter it instantly. Yet Atlas anti-tail holds its shape as if anchored by something far stronger than sublimation. This isn't just visually strange. Mathematically, it's nearly impossible. To maintain its observed brightness and activity, Atlas must be losing mass at around 200 tons per second. Over 2 months since perihelion, that means billions of tons, roughly 1/10 of its estimated total mass. At that rate, the nucleus should be shrinking rapidly, or even disintegrating entirely. But it isn't. NASA's Mars Reconnaissance Orbiter captured Atlas as a bright 932-mile-wide coma cloud, with the actual nucleus inside being only a few miles across. Just 30 to 40 square miles of surface area. Loeb's math says the comet would need 620 square miles of active ice to sustain its mass loss, more than 15 times what physically exists. The numbers don't match. They don't even come close. Normally, a comet losing mass this fast would be falling apart, fragmenting, shedding debris, ripping open fresh surfaces. But high-resolution images from November 11th show a single, intact nucleus. No fragmentation, no debris cloud, no visible chaos. The coma is smooth. The structure is stable. So where is the missing active surface area? How is the comet losing mass at a catastrophic rate without tearing itself apart? This is where spectroscopy delivered an even deeper shock. JWST and Hubble observations in mid-2025 detected a chemical signature that astronomers didn't expect from a comet at all. The gas streaming from Atlas wasn't just laced with cyanide, CO2, and water vapor. It carried a strikingly high ratio of nickel to iron, far above any solar system comet ever observed. Even the Interstellar Comet 2 I/Borisov didn't show anything like this. The nickel to cyanide ratio is so extreme that it resembles the composition of certain industrial nickel alloys. The probability of such a ratio forming naturally is estimated to be under 1%. Then came the polarimetric data, which showed extreme negative polarization at small phase angles, more intense than any comet on record, a signature normally seen in trans-Neptunian objects, icy bodies from the dark outer edge of the solar system. That implies a strange mix of dark grains and icy particles, nothing like the typical dust composition of comets we know. Mainstream comet scientists argue that maybe we just don't understand interstellar comets well enough. With only 2 previous examples, perhaps these exotic values aren't anomalies. Maybe they're normal for objects formed outside our solar system. But this debate won't stay theoretical much longer. On March 16, 2026, 3 I/Atlas will pass by Jupiter at a distance of 53.445 million kilometers, almost exactly at the edge of Jupiter's Hill sphere, where the planet's gravity dominates its surroundings. This encounter is being treated as a natural physics experiment. If Atlas's trajectory shifts in unexpected ways, if its activity spikes or collapses, or if its chemical emissions suddenly change, the event could reveal exactly what this object is and what is powering it. For now, one thing is certain. 3 I/Atlas does not fit any natural explanation comfortably. Every new observation makes the mystery deeper, not clearer. And sometimes the moments when the universe refuses to behave are the moments when our understanding is about to change. What do you think is happening here?